A long time ago in a galaxy far away, NGC 4993, to be exact, two neutron stars collided and created a spectacular light show. After billions of years spent slowly circling each other, in their last moments the two degenerate stars spiraled around each other thousands of times before finally smashing together at a significant fraction of light speed, likely creating a black hole. The merger was so violent it shook the universe, emitting some 200 million suns worth of energy as perturbations in the fabric of spacetime called gravitational waves. Those waves propagated out from the merger like ripples on a pond, eventually washing over Earth and into our planet's premier gravitational wave detectors, the U.S.-built LIGO and European-built Virgo observatories. Yet gravitational waves were not the merger's only products. The event also emitted electromagnetic radiation, that is, light, marking the first time astronomers have managed to capture both gravitational waves and light from a single source. The first light from the merger was a brief, brilliant burst of gamma rays, a probable birth cry of the black hole picked up by NASA's Fermi Gamma Ray Space Telescope. Hours later, astronomers using ground-based telescopes detected more light from the merger, a so-called kilonova, produced as debris from the merger expanded and cooled. As astronomers studied the merger's aftermath in various wavelengths of light, they saw signs of countless heavy elements forming instantly. Astronomers had long predicted merging neutron stars may be responsible for forming elements such as gold and titanium, neutron-rich metals that are not known to form in stars. Most everything they saw in the changing light of the merger's kilonova matched those predictions, although no one definitively, directly saw the merger spewing out gold nuggets by any stretch. Even seen across its estimated 130 million light-year separation from us, the event was big, bright and glorious. Based on the rarity of neutron stars, let alone ones that happen to merge, it is unlikely we will ever see such a display significantly closer to us. But let's imagine if we could, if it happened in the Milky Way or one of its several satellite galaxies. Or, heaven forbid, in our immediate stellar neighborhood. What would we see? What effects would it have on our home world? Would the environment, civilization, even humanity, emerge intact? Although LIGO, by design, can hear the mergers of massive objects such as neutron stars and black holes, astronomers were still lucky to detect this particular event. Ironically, LIGO's exquisite tuning for detecting distant black hole mergers could make it miss big ones occurring around the solar system's nearest neighboring stars. The immense and intense gravitational waves from such a nearby event would probably be greater than the dynamic range of our instrument, Gonzalez says. The amazing thing to me is that you could be so close to black holes colliding, even as close as just outside the solar system, and you wouldn't even notice the stretching of spacetime with your eyes, Gonzalez says. You would still need an instrument to see or measure it. In contrast, a kilonova from a neutron star merger in our galaxy would probably be quite noticeable. Gonzalez says it could suddenly appear as a bright star in the sky and would be clearly detectable by LIGO too. Rather than lasting for a matter of seconds, the gravitational waves heard by LIGO would be drawn out over minutes, even hours, as the neutron stars spiraled ever closer together before their ultimate coalescence. It would be a bit like tuning into a live Grateful Dead jam instead of a studio version. Kari Frank, an astronomer at Northwestern University, says such a large, luminous event could end up obscured by dust and other stars, at least at visible and infrared wavelengths. In other words, LIGO and telescopes looking in wavelengths such as radio or X-ray might glimpse a nearby kilonova that optical astronomers would miss. There have been supernovae, at least ones, that we know of in our galaxy in the last 100 years or so, for which we didn't see the explosion at all, we only saw what was left afterward, Frank says. And a kilonova, for all the punch it packs, is only a fraction of the luminosity of a typical supernova. A star about 8 times the Sun's mass collapsed in on itself and sent its outer envelope of gas out into interstellar space, forming a nebula of heavy elements and other debris, before collapsing into either a neutron star or a black hole. It remains the only nearby supernova astronomers have seen in modern times. Frank has studied the subsequent global campaign to observe supernova 1987A, focusing on how astronomers organized and executed their observations at a time when the internet was embryonic at best. Somebody sees something, and they send out notices to everybody, she says. The people who first discovered it had to phone whomever they could to tell them that this thing was happening, that they saw this supernova in the sky that was really close by, Frank says. For months, astronomers worldwide scrutinized the event, utilizing almost every available telescope. Everybody wanted to make sure that as many telescopes looked at it as possible, Frank says. Eventually, things settled down, but several researchers, including Frank, are still studying the supernova's remnants 30 years later. For some people, it was life-changing, or at least career-changing, Frank says. But not all of them shared in the glory of co-authoring any of the many resulting studies published in the scientific literature. Consequently, there's no real head count of how many people participated. Counting collaborators working on the recent neutron star merger is much easier, some 3,000 authors across 67 papers, or an estimated 15% of the entire field of astrophysics. If supernova 1987A had occurred much closer to Earth, around a nearby star, for instance, the key uncertainty could become not how many scientists observed the event, but how many survived it. According to a 2016 study, supernovae occurring as close as 50 light-years from Earth could pose an imminent danger to Earth's biosphere, humans included. The event would likely shower us in so much high-energy cosmic radiation that it could spark a planetary mass extinction. Researchers have tentatively linked past instances of spiking extinction rates and plummeting biodiversity to postulated astrophysical events, and in at least one case have even found definitive evidence for a nearby supernova as the culprit. "20 million years ago, a star 325 light-years from Earth exploded, showering the planet and radioactive iron particles that eventually settled in deep-sea sediments on the ocean floor." That event, researchers speculate, may have triggered ice ages and altered the course of evolution and human history. A supernova, for instance, can sometimes expel its energy in all directions, meaning it is not always a very targeted phenomenon. Merging black holes are expected to emit scarcely any radiation at all, making them surprisingly benign for any nearby biosphere. A kilonova, however, has different physics at play. Neutron stars are a few dozen kilometers in radius, rather than a few million like a typical stars. When these dense objects merge, they tend to produce jets that blast out gamma rays from their poles. What it looks like to us, and the effect it has on us, would depend a lot on whether or not one of the jets was pointed directly at us, Frank says. If a jet is pointed directly at us, drastic changes could be in store. And we probably wouldn't see them coming. A kilonova begins with a burst of gamma rays, incredibly energetic photons that, by definition, moved at light speed, the fastest anything can travel through the universe. Because nothing else can move faster, those photons would strike first, and without warning. trailing far behind the light, would be slower-moving material ejected from the kilonova. Radioactive particles have heavy elements that, sandblasting the Earth in sufficient numbers, could still pack a lethal punch. That's if the kilonova is close, though, within 50 light-years, give or take. At a safer distance, the gamma rays would still singe the ozone layer on the facing hemisphere, but the other side would be shielded by the planet's bulk. Most radiation happens very quickly, so half the Earth would be hidden, Proctor says. There would still be a momentarily blinding light. For a few weeks, a new star would burn bright in the sky before gradually fading back into obscurity. Don't let all this keep you up at night. Kilonovae are relatively rare cosmic phenomena, estimated to occur just once every 10,000 years in a galaxy like the Milky Way. Usually, a neutron star will receive a hefty kick from its formative supernova. Sometimes these kicks are strong enough to eject a neutron star entirely from its galaxy to hurtle at high speeds indefinitely through the cosmos. When neutron stars are born, they're often high velocity. For them to survive in a binary is non-trivial, Proctor says. Any local merger of neutron stars at all would take LIGO by surprise, given that the events are so rare and astronomers might not even see the resulting kilonova at all. But if one did occur, say, in one of the Milky Way's satellite galaxies, it would be a great reason to run to a telescope to witness the flash and fade of a brief, brilliant new star. The dangers would be nearly non-existent, but not the payoff. Our generation of astronomers would have their own supernova 1987A to dissect. This is a once-in-many-lifetimes kind of event, Frank says. Thus, she says, we would need to follow something like it with all the world's astronomical resources. We have to remember to think beyond the initial explosion, she adds. Stuff might still happen, and we have to keep a watch out for that. When our view clears, in December, many of the world's telescopic eyes will again turn to the small patch of sky containing the merger. In the meantime, papers will be penned and published, careers minted, reputations secured. Science will march on and wait for the next possible glimpse of a kilonova, the whispers of a neutron star merger, or, if we're lucky, something new altogether.